All right, we're going to look at how we set up a simple harmonic motion problem and the reason why we set it up this way. So it turns out that if you have a situation where your acceleration is proportional to the negative position function, okay, or same kind of thing but in an angular sense, so my angular acceleration is proportional to my negative angular position. If that is my situation, this is the form of an equation that works where I have x is equal to a, which is going to be our amplitude, cosine of omega, which is our angular frequency, times the time plus phi, which is our phase shift in our kind of equation. So here's why this works, why you would want to use this form of an equation if you run into this type of situation. So I have a position function. I go ahead and get a velocity function, so I take the derivative, okay, and so I get negative a omega, so I take the derivative of what's inside, yep, you remember this, sine of omega t plus phi. Okay. I take the derivative yet again to find my acceleration function, so I get negative a omega squared cosine of omega t plus phi. And what you're hopefully going to see here is I see that I have a negative a cosine omega t. Oh, I see that a cosine omega t plus phi term, and I have this negative omega squared. So what I get is I get a is equal to negative omega squared times a cosine, but instead of writing all that stuff underlined in blue, I'm just going to write x. And so I get this form for my equation. So it works. So I can get that requirement met using this base. Okay, so let's talk about what each one of these parts are. So A is telling me about the amplitude. Amplitude is going to be our max displacement. Omega is our angular frequency. Actually, I'm going to do phi first. Phi is our phase shift. And omega is our angular frequency. Now, something that some people get confused with here is angular frequency is not the same as an angular velocity. So be very careful if you do this in the angular set that this is omega angular frequency, not the derivative of this, the angular velocity function. Okay, angular frequency is going to be a constant. And I have linked down below 4 videos on how to find the angular frequency in a simple pendulum, a physical pendulum, a torsion pendulum, and a mass spring setup. Okay, so angular frequency, you find that depending on your situation. And again, those videos are linked down below. These are conditions, okay? So you build your equation based on the conditions. So let me give you an example, okay? So let's say I have a mass, and I go ahead and I push it up against a spring on a frictionless surface here, and I'm going to release it, okay? Now, this spring is attached to it, so it's going to just kind of bounce back and forth. And I want to say, all right, what are my things going to be? So amplitude is the max displacement. So you see that I've pushed it back 5 centimeters. So that means my amplitude is going to be 0.05 meters. Okay, it's my max displacement. Okay. To figure out my phase shift, okay, to find the phase shift, what you do is you kind of say, well, what is the condition I know? So at time 0, I know I'm at this position, negative 5 centimeters. So I know that x is equal to negative 0.05 meters at t equals 0. So I go ahead and I plug that into my equation. So I say, okay, I got negative 0.05 equals my amplitude, 0.05, times the cosine of omega t plus phi. And omega t is gone because time was 0. My 0.05s cancel out, and so I'm just left with negative 1 equals the cosine of phi. And then I solve for phi. Now we will want to be using radian mode when we are plugging this in, so make sure you're on that wavelength. And so phi comes out to be pi radians here. And that would be how you would find your phase shift. So use some conditions that you know about, the position at any time, and find that. Another one that pops up is if you want to find a maximum acceleration or a maximum displacement, and you can think about those maximums occurring when the cosine of omega t plus phi is just 1. So the maximum x is a. Okay. The maximum velocity occurs when the sine of omega t plus phi is 1 or negative 1. And so the maximum velocity is a omega. I could probably write this down here. So I have x max equals a, v max equals a omega, and a max equals a omega squared. Okay, so you can find those maximum values by just making that cosine equal to 1 or negative 1, or the sine equal to 1 or negative 1. And so you could solve for when that time is. I will tell you that the maximum acceleration occurs at the maximum displacement, because both of those have the cosine function. Okay? And when that cosine function is 0, so at the equilibrium position for the spring situation, my velocity is a maximum. Okay? So they just kind of alternate back and forth. Okay? So that's it for setting up our simple harmonic motion. Again, if you want to watch the angular frequency, figuring that out for different situations, follow the links down below.